Okay, so we are discussing the magnetic elements and we are trying to understand how the flux and force or torque can be computed. And from this, we have gone into understanding the BH curve and then further how all this is utilized for operation of a motor, something as a motor such as a reluctance motor. So this basic understanding what we have got yesterday, that if let us say we have a simple C core electromagnet and we are trying to excite this coil and this plunger moves, effectively what is happening from the magnetic point of view. So we are trying to get the work done, and which is basically this area within this triangle, which is the difference between what is the present flux linkage and the final flux linkage. So that's the, and keeping the current constant. So that's the kind of area we are getting over here. And whatever is remaining, this upper triangle, that is basically transferred back to the source. This is only required for magnetizing the core. So same principle we have seen that is used for switched reluctance motor also, but we can utilize basically the core better if we go up to the saturation limit of the core. So this is better utilization we are making. Of course, we have bigger area which is coming as the mechanical work done. And if let us say load is not enough and you want only some light load to be operated with this, you need not operate it completely up to the full current limit. You can operate for 50% current or 1/4 of the current. That's all fine. Now somebody may argue that if the saturation is extending the area and we are able to get more work done, why not get twice of the current where it is going into deep saturation? So the problem is that first of all, in the proportion in which you are increasing the current, the work done is not increased in the same proportion. Second thing is that you need much thicker conductor to carry the double of the current. And third thing, because this is a rotating, a rotational quantity over here, or rotational, what to say, plunger over here, we also need to demagnetize it quickly. So if we move deep into the saturation, it is difficult to come back quickly to zero. So we might get a chance that it might happen that it would apply positive torque as well as negative torque while the inductance is changing to negative side. So this is what we have tried to see, and we tried to plot the inductance also with respect to theta. And what we are finding, so here the torque, we have written the final expression for torque. It is basically half I square times of dou L by dou theta. I is basically coming as I square. So direction doesn't matter here. Only the value should be non-zero and there should be changing value of inductance. So if this dou L by dou theta is positive, we get a positive torque. If dou L by dou theta is negative, we get a negative torque for a given current. Now we try to plot the inductance for this system. So what is there? Inductance is minimum when the plunger or the rotor is aligned along this axis, which is theta equal to 0, and it is maximum when it is aligned along theta equals to 90 degree. So these two positions we are naming as unaligned position and aligned position. These are the two names we have given, and this is how the inductance is also changing. For the unaligned position, it is at the least value, then it is changing. Theoretically, it should change linearly and go up to the maximum and then come back to minimum, then again go back to maximum and so on. It will keep rotating. But practically what we will have that when we are at the extreme positions, let's say at 0 degree or 90 degree, slight change in position would not change the inductance much. So which is why what we will have, the curve will be a little bit flat on the near these extreme values. So little bit flat you can make, that will be near practical thing. And actually if you see, it would be like a smooth curve which will be linear in this zone in the middle and a much flatter portion towards the top and bottom of this curve. So something like this it will be moving. So effectively we have a zone where inductance is varying almost linearly. So dou L by dou theta is clearly a positive value, non-zero DC value you can say. Then for the next segment, this will be a non-zero negative DC value, and so on. It will keep alternating dou L by dou theta. Now, if you keep a constant excitation, let's say this blue current we have drawn, if this is extended continuously from full throughout the rotation, what we will have? We will have alternating torque generated on the machine. But if we want to have only positive torque, we need not apply the current during minus dou L by dou theta. That's what we have shown. The current applied during this positive dou L by dou theta, indicated by blue color, would generate the positive torque only, indicated by the blue color. If you wish to generate negative torque, you apply during this zone, which is minus dou L by dou theta, which will generate basically a negative torque. So I will put that in green color. So this will correspond to this torque, and that will have effectively a average value, negative average value of the torque. So this basic functionality you have understood, right? For switch reluctance motor.
Yes, sir.
Yes, sir.
Okay.
Yes,
Any questions you have up to this point?
Sir, like what is, like, just one clarification I want to understand. What is the type of magnet we will use? Because if you use soft magnet, then it will be easily like magnetizing and demagnetizing. But why we are going for hard magnet here?
We are not going for hard magnet here. It's not magnet, basically magnetic material.
Yes,
we
sir,
don't want any coercivity here, right? This is all done
yes,
with soft magnetic material.
okay.
Hard magnetic materials are required when you want to make magnets which will retain their coercivity, and the remnant magnetic field will be something, and then coercivity will be large. That is what we have seen, this kind of curve and these different kind of magnets. This is all made up of hard magnetic materials. Or if we have self-excited DC motors where we need some residual magnetism intentionally, those places we need to go with hard magnetic material. Here we don't need. Actually, hard magnetic material would be difficult to handle in this case. Fine?
Yes, sir.
Okay, now if this basic understanding you have got, let us go for a little bit more practical SRM. So if, let us say, first thing is, if we have to define the type of SRM with this structure, so what this will be, there are 2-3 things which we need to mention when we are writing about SRM or giving definition for the SRM. First thing is, how many number of phases are there? So that thing, and then what is the number of stator poles divided by number of rotor poles. This information we need to provide for SRM motor to define it properly, assuming that the poles are distributed symmetrically. So in this case, what we have basically, these two poles are getting formed because of the same phase. So this will be connected in series and it will have 2 terminals only. So it's basically a single phase SRM with 2 poles on the stator and 2 poles on the rotor. So single phase 2x2 SRM, that will be the definition of this motor. Do you understand this point?
Yes, sir.
And another thing what we can say is, what is the step angle for this SRM? Because when we are exciting the current for, let us say, this particular phase, we are not exciting continuously. We are exciting here, then here, then here. So there is some gap. So this can also be seen as in what step size this SRM is moving. Okay, the step may be from here to here, or maybe just from here to flipping back. That may be another step. So that is defined by what is the stator pole pitch and what is the rotor pole pitch, the difference of the two. Stator pole pitch is nothing but 360 by number of stator poles and 360 by number of rotor poles. It's the magnitude either could be higher. Your number of stator poles could be higher or number of rotor poles could be higher. This will be your step size. So here step size would come what? It would come 0. The problem is that because this has tendency, if you keep applying this thing, this particular phase, if you keep exciting, it will get stuck over here. Okay, that's why we need better SRMs and which has the capability to move continuously. So let us see a simple structure, at least little bit more number of phases, more number of poles. So what we try to have basically in general, the NS by NR ratio, this should not be any integer. NS by NR or NR by NS. These both should not be integer. This is what we should avoid generally. Although there are motors which are made with integer number of ratios also, but generally we should avoid. So this is one typical case of integer or integral ratio. And this is what happens, you see. This is the tendency to get stuck. You have no other phase to excite and take it out from that mode. Understanding my point? Okay, now let us try to go for more number of phases. So let's say we have one phase over here. So what I have drawn is basically 6 poles on the stator. We will also learn how to classify the number of phases or how to understand how many phases are there total. Now let us draw the rotor with say 4 poles. So what we may have is basically something like this. Fine. So these may have windings like this. So this is a typical SRM which you can say is 6 by 4. Now 6 by 4 is not an integer. So basically what it means that there is no condition for which this will get locked out. Okay, we will see how. Now let us say if we classify the phases, right, how the different phases are coming over there. Say the motor is rotating in this direction. Okay, speed could be anything. Now, if it is rotating in this direction, we can classify all these poles in 3 different groups. One group is that along which this rotor is aligned. Say this is phase A. Correct? Then another phase is there along which this is going to align, because once this moves by certain angle, this will get aligned along this, right? So these phases can be grouped as say B. Are you getting my point?
Yes, sir.
And the another set of coil from which this magnetic rotor is going away. So this is going to go into complete unaligned position when this moves another 15 degree and this moves another 15 degree, this will exactly be in the center of the rotor. So this you can call as phase C. So based on the position of this rotor, or if you see from the rotor point of view, these stator coils would look like in three different groups. One group where it is completely aligned, another group where it is going to get aligned, and another group where it is going away. So this is the way how you group the different phases in any motor, group the different coils. So this is kind of three-phase SRM. It has three set of coils. One set at any moment, it is aligned, it is going to be aligned, and it is going away. Are you able to visualize that?
Yes, sir.
Fine. Now, when you have 6x4 or 4x6, this kind of arrangement, see, even if this is aligned and stuck over here, the next moment you excite B and remove this excitation A, this will have tendency to automatically move. Understand my point? Which was not there in the previous case. In the previous case, what we had, if it gets stuck here in this position, there is no way to move it further. You see the problem here? This is the difference when you have integer and non-integer ratios. Of course, there are motors with integer ratios also, but they are operated with certain conditions. So the control ensures that Yes, Deepak?
If we reverse the direction of current in A dash, let us say in previous case, then because of repulsion, it will move forward, na, sir, if it gets stuck.
See, this is the torque expression. Direction of current does not matter in SRM. The only thing matters is whether you have changing inductance or not. If your inductance has saturated, which means either the maximum position or the minimum position, you don't have any dou L by dou theta. It is stuck. You cannot generate any torque. Understanding my point?
But physically, if we see, sir, like if there is a magnet there and if we create opposite polarity,
No.
then it should have.
SRM doesn't have motor. This is reluctance motor.
Okay, this is non-magnet.
Yes, this is only reluctance motor, which is working on the principle of reluctance. I have not introduced the magnet so far in this.
Oh, understood.
Okay. Now we have understood how to group the different phases, how to count number of phases. So you can make any number of coils in this, and you can see that based on the position of this rotor, how these coils are coming. Whether something is aligned, something is not aligned, something is partially aligned, or something is going away, or something is going to get aligned. So these things will classify and tell you how your coils are grouped together. So these two coils are grouped together. These can be connected in series. So two terminals could be there for this. Similarly, this B and B can be grouped together. So two terminals can be taken out, and C can be grouped together. So these two terminals can be taken out. So totally you will have 6 terminals, which says that 3-phase, and then number of stator and rotor poles are there. Now here we can see the step angle. So what we have said, basically the difference of theta s and theta r, which is nothing but 360 by 6 minus 360 by 4. So this comes as 30 degree. It could be 4 by 6, which means 4 on the stator and 6 on the rotor also. Still the step angle would be this. Understand my point?
Yes, sir.
Okay. Now let us see how the inductance for all this can be drawn and how you will have the excitation. Okay, same way we will follow the same procedure how we have done for 2x2 motor. We have the inductance for 3 coils now, LA, LB and LC. And all will have some maximum value and some minimum value. Now, the only question to understand is, say, we take any axis you can take as reference. Say I'm taking here theta equals 0 degree. Now from here, how these coils are or how these inductances are going to change. So when we are at theta equal to 0, our LA is maximum. This reluctance is minimum. This is aligned along this. And V will become maximum after 30 degree. You see this point? Once this rotor moves by 30 degree, this will get aligned. And then this LB will be maximum after 30 degree. And LC will be minimum after 30 degree because this will get aligned exactly in the middle of the two poles of the rotor. Understanding my point?
Yes, sir.
And again, once this rotor position moves from here to here, again this A will become maximum. You understand my point? So overall, what we can do for simplicity, we can have intervals of 30 degree. That is our step angle also. Correct? Now what we have said that LA is at maximum. So this is interval of 30, 60, 90, 120, 150 and so on. It goes for up to 360. But we will understand within this only what is happening. Now LA is maximum here, and after 30 degree what will happen? This will be in a position where this pole will be at 30 degree, rotor pole, this will be aligned here. So which means it is somewhere between the LM max and LM min. Another 30 degree movement and this will come at the minimum. You see the difference? Or another 15 degree rather. You understand this point, what I'm saying? Yes or no? Say quickly.
Yes, sir.
Yes, sir.
Sir, one second.
Think and tell, because if you are able to draw this LA, LB, LC, that's all. That's the whole thing. So that is why think carefully what I am trying to say. Let us draw one by one certain positions here. Right? We have the poles. Let us say A is here, B is here, C is here, again A, B and C. And we have the rotor positions like this. Fine. This is okay, right? This is easy. So A is aligned. Aligned means the value for LA is maximum. Now, if it moves by 30 degree, okay, what's happening? Okay, fine. Now, if it moves by 30 degree, your rotor will come something like this. See, this is not the minimum position for A. You see this? Still, this is somewhat closer. And there is possibility that for a position like this, which is alignment along C, this will be the minimum position for A. You understand my point or not?
Yes, sir.
The rotor has rotated from this to this and now here. So in response, what will happen? I think let me draw once, then you try to understand what is happening. Okay. Now you try to correlate how with the rotating positions the LA and LB and LC are changing. Okay, for this theta equals 0 degree, what we have, LA is at the maximum. And when it moves 30 degree, LB would be at maximum. Another 30 degree, then LC would be at maximum. Understanding my point? Okay.
Yes, sir.
Now, this process only repeats. If you go by this understanding only, that every phase is coming at maximum after 90 degree, because that is the rotor angle. After 90 degree, every phase is coming at maximum. If you go by this understanding alone, still you will be able to understand this graph. Because that is what the angle of rotor is. No, every 90 degree it will get aligned to one of the phases. Fine, right?
Yes, sir.
Yes, sir.
Yes, sir.
Getting or not? You tell me clearly.
No, no, yes, sir.
Yes, sir.
Tejdeep?
Yes,
Not
sir. Clear.
from you. Is that clear or not?
Yes, sir. Clear, sir.
Clear? So this is what we have drawn, the ideal inductance for this motor. But actually in practice, it will be slightly smooth. You can say like a flat structure here, and then this also flat. So this green colored waveform would be the actual shape of this inductance. A more practical. So if you see practically, you will have only this middle of this phase where you can apply any current, because that is where you will have a linear dou L by dou theta for any phase. Let us say for A or B or C, that will come in sequence. But if you see, this is the zone where one of the phases will come as linear. Now which one we have to apply, that is dependent on which one is giving me positive dou L by dou theta or negative dou L by dou theta if I want to apply negative torque. So this chart has become little heavier, making it difficult to move. Let us extend this quickly and then we summarize this. Okay. Different intervals I have drawn. Okay, still my 0 to 30 degree step size is intact. Now what is happening during this interval? During this, what I have drawn as the intermediate, one of the phases will have linear and positive or negative slope. For example, B is having positive slope, whereas, so little bit on this side, A is having negative slope. So if you draw dou L by dou theta, this will be negative. Similarly, dou LB by dou theta, this will be positive during this. So I think for B, this zone should be chosen, not this one. So it will come here. Then B will again come positive, or sorry, the linear zone will come somewhere in the end. So this then becomes flat. You need to put the scale, it seems. Okay, fine. Last few days of online teaching will give everything. Okay. It's getting stuck. Sorry for the glitch. I don't know what's the issue. Let me close it. Some problem with whiteboard, it seems. Okay, I'll get rid of some content here. It has become too bulky actually. Fine, at least some things are there. So okay, good. So meanwhile, you can draw and you can see how it is coming on your own. Perhaps the improper division of angles has given some confusion. think that's enough. Fine, we have got 30, 60, 90, 120, 150. We have LA, LB, LC. Let's say this is the max, this is the min, this is the max. You understand this, right? How I am drawing this? Fine, right?
Yes, sir.
Yes, sir.
Yes.
Okay. So what I was trying to say is that whenever you have this kind of ideal inductance characteristic, basically this will not be so practically. It will be flat on the near the max and min positions. So here also you can consider like this and this. Everywhere it will be the scenario for all three inductances. So basically we cannot have much torque developed during these zones, the Lmax and Lmin zones, because it's almost flat kind of characteristic over there. Where we can have is this zone, which is kind of linear. So what we can do, we can divide this linear part only. Say if I am taking only positive slope, so this comes the positive slope for the B phase. Similarly, for the A phase, it will come over here, this zone. For the C phase, it will come over here, this zone, which is coming between the maximum and minimum zones. That linear portion we are trying to take out. Again, we will have that kind of slope here. So if you see that it's coming in sequence, positive for B, then positive for C, then positive for A, again positive for C, and then this positive for C. This we are trying to generate positive torque. If you do for the negative torque, again you will see that it's going in the reverse sequence. Understanding my point? Now it is coming A, B, C, then A, B, C, and so on it's going. So what we need, basically we need to know these positions for which these particular coils A, B, and C would be excited. That's what I was trying to tell. So now we know that where our dou L by dou theta for a particular phase is going to be positive. Say B is here, then okay, this is negative, yeah. Then C is coming over here. Say C I draw in blue color, and R I draw in red color, so that is coming over here. So these will be the excitations for different phases also. These will be the zones of excitation for different phases also. So these boxes which I am coloring, this is the duration for which this particular phase is excited. And then you have torque generated corresponding to that phase. So A current is applied only during this zone, and then it will be applied next over here. So there is clear gap of 90 degree. That's the meaning, right? The rotor is having 90 degree angle. So anything will repeat only after 90 degree for any phase if we are talking about. Am I clear?
Yes, sir.
Yes,
Correct?
sir. Yes.
So we are not continuously exciting any phase. We are giving current only at a particular position. When the coil is between 60 and say this 75 degree, then we are exciting phase A. That's all. Next we wait for the next sequence. Then after that, it is our phase B which is excited. That is 90 degree and 105 degree. Then again we go for phase C, 120 and 135. So these kind of repetitions would come for any given phase. Understanding my point?
Yes, sir.
Yes, sir.
Okay. Now, ultimately, what we are trying to do for any SRM. So we have understood how to classify the SRM. That means how it is defined. So first we should know how many number of phases are there. Then how many stator poles divided by how many rotor poles. This will define basically the step angle for the SRM also, if we are operating in this traditional manner. Okay. Now, the only thing we have to understand is how are we going to inject a constant current pulse. Let's say this is IA. We are injecting some pulse here. Then after certain duration, we are again injecting a pulse. Then after certain duration, again we are injecting a pulse. How are we doing this? The next question comes over here. How do we do that? How do we maintain a constant current level? You have understood the machine, but now you have to run it. You have to control it. For that, we have to inject constant current pulse. So how do we do that? What's the way?
By using H bridge.
Yeah, that is one correct answer. But H bridge is just the, it is connected across the device. How do we inject? By there I mean that what is the control method by which we are doing this? Okay, so this answer is okay for starting this. Let us say first we need to model this. What we are trying to do? We have a coil basically. We have a coil for a given phase. Let's say this is connected in series. So ultimately what we have? We have a coil in which we are trying to maintain the constant current value. Say this. Now this coil has property, inductance of this coil can change because that's what is happening in the reluctance motor. The inductance is changing from minimum to maximum value, and that is why this is not a linear system. Understanding my point?
Yes, sir.
This is one problem. Now what we do, bare minimum to start with that, okay, we can connect some voltage source converter kind of arrangement for injecting some current. And we can control that by turning on, turning off the switch. For example, if you connect half H bridge in this manner, what will happen? If you turn on the top switch, the current will basically rise in the coil, right? And if you turn it off, what will happen? It will fall.
Hysteresis type control.
Correct. So for the non-linear system, if you try to have something like PI controller or some other linear controller, it would be difficult. And I don't say that it is not done. People have done on this side also. People have worked on this side also. But a more conventional way or more easier way could be we utilize this property only for this particular system. Whenever we do apply some voltage, there is a rise in current. Whenever we remove the voltage, basically the current value falls. If we are able to maintain that within a given band of current, let's say current is only going between these two bands. If we are somehow able to operate these switches, that current is always maintained within this band. So we can have some upper limit, we can have some lower limit. Then effectively we will be injecting a constant value of current. And this is too much exaggerated actually. It's not, normally it's not so wide. So it's very, very close, and the average value is what is injected in the coil, which basically works for generating the torque. So this is what is known as hysteresis based control. This is the hysteresis band. Similar to, we have seen the magnetic BH loop, right? Where we have hysteresis. The meaning of hysteresis is memory. We should know what was applied earlier and not what now next what should be applied. You understand my point? For example, if let us say you have got the indication at this point t equals 0, that okay, now you have to apply current for A phase. So what you do, you turn on the top switch. What is the configuration for this system now? This is the configuration for the system. Correct? This is the configuration now. So what will happen? Current will start rising. Now in your controller, you have fixed certain upper limit that okay, when this current is glowing, you have the complete feedback of this current, continuous feedback for this current. So when this current is rising, you have some upper boundary beyond which it cannot go. And the moment it touches the upper boundary, what you do? You switch the circuit to the next mode, which is basically turning on the bottom switch of half H bridge, and it becomes like this. So due to the resistance in the coil, it will decay slowly. But what you do, you fix the lower limit also, that while it is decaying, it cannot go below this lower limit. The moment it touches the lower limit, again you switch back to the mode 1. And again it rises and hits the upper boundary, and then it falls. And once you have to switch off, you allow it to slow down and come back to 0.
But sir, in this case, then during lowering down, we are not having control. But if you want a specific timing,
I will come to that. So
yes,
this is one way. Now, what logic you have to use over here is that you need to know what you have. Let's say there are two states. One state where you are applying some positive voltage across the coil, and second where you are simply shorting the coil. There are two possibilities only, right? So what will happen? You need to know if your state is equal to 1 and current is less than the upper boundary. What you will do? If this is the condition and current is less than the upper boundary, which means what you have to do? S remains 1.
Yes, sir.
Correct? This is the if condition. If S is equal to 1 and I is less than IU, or I write in two-step if. Two-step if means if else inside another if else. So if S equal to 1, then if I is less than IU, then I keep my S equal to 1 only. There is no problem, it is rising. Now else for this if it is hitting this boundary, going beyond this, what I have to do? I have to make S equal to 2. I have to come to second state. This I am writing the control logic, what you have to apply. This is not a linear control, right, where you have to model and do. Here we are simply applying on basis of what states are available and how we are operating this. You understand my point?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Now the second, the else condition. Else means if the state is 2. If the second state is applied and you see that current is, say, when you are in second state, you will check the second boundary. Current is greater than IL. If, then nothing to do. If it is greater than IL, you continue to be in that state. Else, if you are crossing this boundary coming below, then immediately you go for 1, which means now you switch to this. You understand my point? This logic what I'm writing over here is basically your hysteresis control for the current. You are operating your current within certain boundary of upper and lower limit. You can decide if nominal value of current is I, you can decide what is value of IL and IU. Understanding my point?
Yes, sir.
This is one control method with which the current can be maintained to a certain level. Similar to DC-DC buck converter. That is what we are trying to do. We are trying to maintain a value of current by switching the converter on and off. And it's going. Now the problem which Deepak has just now mentioned, there is no control when we are trying to decay the current. This is simply shorted. That means it is at the mercy of the resistance of the coil. If resistance is too small, let's say tending to 0, then it may take a lot of time in discharge. Which means when we have to switch off the coil, it may not come back to 0 for a very long time, which is not correct actually. You understand the problem? Here it is fine. It is coming down slowly, okay, it is maintained within the boundary. But when you have to switch off, then this would be a problem actually. So we should have control for the turn off also. That is where you can go for full H bridge. You can connect the coil in this manner. That means the terminal A and A dash you can connect in this manner. Now your gating signals could be like this. If you turn on the switch, which means the switch, this one and this one, the top on the left hand side and bottom on the right hand side, then your configuration is like this. And when you connect in the other mode, it is like this. So here you have control, equal control for both the modes. Mode 1 also you are controlling the current through this VDC, and here also you are controlling the current through this VDC. We are not operating for bidirectional current. That's not the purpose. The purpose is to have good control. That's why this negative voltage is applied across the coil. Now what will happen? The decay and rise this time will be equal. So it will rise quickly and then it will quickly jump between the two states. The logic remains same and quickly it will drop down to 0 whenever required. Logic remains same. You operate in either this state or this state. Now here what is the disadvantage? The disadvantage is that within this boundary or during this time period, you are switching so many times quickly. See, going faster and coming down faster is required. But when you are within this boundary, it is not necessary to switch it down quickly within this. You understand my point? Somebody would say I can use mix of that. I will rise faster and then I will decay slowly. And then I will rise faster and decay slowly. And then rise faster and decay slowly. And whenever I complete this cycle, I will come down quickly. So these different modes of decay are defined like either slow decay or fast decay. Slow decay means you don't have any voltage applied for the reduction of the current. It is at the mercy of the resistance of the coil. Fast decay meaning you have a voltage which is responsible for reducing the current. These terms are basically more popular when you talk about companies like Texas Instruments and all. These terms are more popular over there. So their data sheets and all, if you read, they will have these kind of things indicated over there: slow decay, fast decay. This is the terminology what they are having. So if you have 3-phase motor to operate SRL, you will have 3 full bridge converters. 3 H bridge you will have. Or sometimes you may connect only 3 half bridge and all the second terminals connected to the negative DC. but there we will lose the capability of fast decay. You understand the point?
Yes, sir.
Okay, so maybe just a quick look into the one of the TI data sheet that may give some insight to you. You have any class now? I'll just take 5 more minutes.
Wave lab.
Yeah.
The lab. Wave lab.
I did not get. Please speak clearly.
Sir, we have DSP lab from 4 to 6.
Okay, just 2 more minutes and then I will close this. So I'm trying to see where I have kept. Okay, this is one IC, basically some things they have given. So this is actually done for different motor, which is called stepper motor. So which is basically combination of kind of your SRM and another motor, which is BLDC. So they have this kind of application of voltage across the coils. Sometimes they may have 3 terminals. So one they will connect to the supply, other 2 they will keep toggling between this kind of structure they may have, or they may have a simple A dash B dash kind of connection. So these are done for basically ensuring that you have slow or fast decay kind of arrangement. Understanding my point? Okay, so here we have seen lot of things about particular class of motor where we have the winding which is basically concentrated about a particular pole, or we can say this is lumped winding machine. Another lumped winding machine is basically BLDC, where again we have similar this stator structure, but on the rotor instead of simple magnetic material we have magnets. So we may have north south this kind of magnets. The structure is very similar except that magnets are placed over there. And then what we have basically, when you rotate the rotor, you will have some back EMF generated on the coils, which looks similar to the actual DC motor, DC EMF kind of thing. And there also we need to apply current, which is again pulsed in the manner, in the nature. So EMF may be trapezoidal in nature, which is going something, let us say, like this. And you will be applying current during this zone where the EMF is flat. You apply a pulse current, but here you should have capability to even invert the current also. The power must be unidirectional. So here for BLDC you will have bidirectional current flow. So definitely full H bridge is required. And the control philosophy will remain same. The control methodology will remain same. So then half H bridge cannot be useful in case of BLDC. In case of BLDC we must have full H bridge because we want bidirectional current. Fine. So I'm not going into too much details of now BLDC and all, but what we will have now onwards is basically machines where we have distributed winding. So instead of lumped winding, what we will have the windings going in a distributed manner, so that if let us say you have magnet on the rotor and you rotate this thing, you will find a sinusoidal voltage output at the terminal. So these kind of motors we are going to deal with next. Okay. So any quick questions you may ask, then we will start tomorrow for these different motors.